Today's a big day. We finally get to learn the burning question in your mind. What is a logarithm? I know you've been dying to know. So a logarithm is really just an exponent. It's a different way to write an exponent. So we just kind of remember our exponents. Like really quickly, what's 4 squared? Right, 16. 4 to the 0 power, 1. 4 to the negative 2, 1 over 4 squared, or 1/16. 4 to the 1/2. Now we know is square root of 4, which is 2. And then in a last minute twist there, the 4 to the negative 1/2 would be 1 over the square root of 4, or 1/2. So in a logarithm, this is how we would say this. We would say the log base b of c is x. The log base b of c is x. And these two expressions are the same. Different ways to write the same thing. So we've got some different parts here. So here on both things we have a base, and the base is always positive. Base is always positive. Then we have our x, which is our exponent. And the exponent can be positive, negative, 0, fraction. The exponent can be anything, as we saw kind of up here, right? And then the answer is the c. So c here is the answer, and the answer is also always positive. A positive number raised to any power, it's like a positive number raised to any power is always positive. Okay, so if I gave a quick example of what that might look like, that might be like something like this. Let's see, the log base 10 of 100 equals 2. And that's the same thing as saying 10 squared equals 100. Log base 10 of 100 is 2 is the same thing as 10 squared equals 100. So here we have some exponential equations that we know to be true. We know that 3 squared is 9, and now we're going to rewrite it. The log base 3 of 9 is 2. Just getting used to the log notation. The log base 5 of 1 is 0. The log base 5 of, 1/25 is negative 2. The log base 8 of 1 is 0. Now we're going to reverse it. We're going to rewrite each log as an exponent. So we're going to do something we call log loop it. Log loop it. So we log loop it like this, and this would rewrite 6 squared equals 36. Or here, 49 to the 1/2 power equals 7. Here, if we log loop it, we get 2 to the negative 3 power equals 1/8. And then this one actually has a mistake. It should be 4 to the 0 power equals 1. Obviously not 4 to the 1 power equals 0. So log looping it. Here we log loop it, and then we can kind of just figure it out in our head, right? 2 to what power gives you 64? 2 to the 6th power is 64. 9 to the negative 1/2 power equals x. What's 9 to the negative 1/2 power? Well, 1 over the square root of 9, which is 1/3. Next one is b squared equals 16, and the b is just going to be positive 4. Not plus or minus here, because the base is always positive. The base is always positive. So this next one, without the equals x, people get confused. So if you add the equals x, then you're like, oh, I get it. 5 to what power gives me 125? 5 to the 3rd power. These last two definitely need that equals x, because these are a little bit trickier. 6 to what power gives me 6 root 6? You're going to be like, I have no idea, right? Well, think about 6 is 6 to the 1st, and square root of 6 is 6 to the 1/2, right? And what happens when you have, multiplying powers, you keep the base and add the powers. So 1 plus 1/2 is 3/2. So x here is 3/2. Similarly here, 2 to what power gives me the cube root of 1/4. So 1/4 is 2 to the negative 2. And then the cube root is 1/3 power. So 2 to what power gives me 2 to the negative 2/3? That's negative 2/3. Negative 2/3. We're going to go to the next page too with just some more stuff on logs. And a lot of this is just really intuitive. Like logs are equal if you have the same base, like here, and you're taking the log of the same thing. So 2x plus 1 has to equal 3x minus 6, or x has to equal 7, right? Here the bases are the same, so we would set x squared minus 1 equal to 8. Now here, when we square root both sides, we are going to have both plus or minus because they both work to give me positive 8. I do have to take the log of a positive number, but negative 3 squared minus 1 is 8. That's different than over here where we just did 4, and that was because we were solving for the base, and the base had to be positive. So that can be a little tricky. Here we're just showing that the statement is true, so we're thinking about 3 to what power gives you 27? Right, 3. 3 to what power gives you 3? Right, 1. 3 to what power gives you 81? Right, 4. Is 3 plus 1 4? Yes. Not a lot of writing, but just kind of that thinking. And this is really setting us up for our next lesson. 6 to what power gives me 36? 6 squared. 6 to what power gives me 6? 6 to the first. 6 to what power gives me 6? 6 to the first. So 2 minus 1 is 1. Here we have 4 squared is is 16. And then 4 to what power gives me 4 is 1. Is 2 times 1? Yes. This 1/3 just kind of stays there. 5 to what power gives me 25 is 2. The 2 just stays there, and then think about it. 5 to what power is the cube root of 5? You can write it down if you want. Right, 5 to the 1/3 power. So 2/3 and 2/3 are equal. Those might not seem like hard problems or like what's the point, right? But that's setting us up for our next lesson. And then we have funky log things, which everybody gets the first funky log thing. 7 to what power gives you 7 to the 4th? X is 4, right? Obviously. But a lot of times we see that without the equals x. We see it like that. So if you add the equals x, then you'll get it right away, that it's 4. And it's always going to be the same number here and here. So like it might be the log base 19 of 19 to the 32nd power. Well, that's going to be 32, because 19 to the 32nd power is equal to 19 to the 32nd power. This one gets people. I'm going to tell you off the bat that the answer is 11. I call this problem odd man out. So whatever the odd, like you have a 6 and an 11, the answer is the odd man out, the 11. But here we can solve this by rewriting as a log. Rewrite as a log. So think of this, instead of being 6 to the 6, log base 6 of 11, let's think of it, for example, as 6 squared equals x. Then we would be like log base 6 of x equals 2, right? 6 squared equals x. Same thing, but now we instead of a 2, we have this log base 6 of 11. So 6 to the log base 6 of 11 equals x. This is the log base 6 of x equals, remember that 2 just went there, so the log base 6 of 11 goes there. And then you're like, oh, so clearly x is 11. You don't have to show any work for that problem. You can just do it by the odd man out, but you can think about that for a little bit and figure that out. That's a little bit tough to think through. And then the last thing is our graphing of logs, right? So we might have even graphed these already. So if I rewrite this as an exponent, this is 2 to the y equals x. So I can make an ordered pair table, but I'm really choosing the y's first, right? And 2 to the negative 2, 2 to the negative 1, 2 to the 1, 2 to the 0, 2 to the 1, 2 to the 4th. So my ordered pairs are like 4, 2, 2, 1, 1, 0, and then it kind of goes in like this. So that is the log base 2 of x. And then here we're introducing for the first time the natural log. The natural log is the log base e natural log equals log base e, and we will circle back to that later in the chapter, but this is e to the y equals x. And remember that e is 2.718 to the y equals x. And that would generate a lot of decimals if I did a t-table, but it would definitely go through the 0.01, right, because e to the 0 power is 1. And then this is just going to be slightly steeper than the log graph. And we're not even going to be really picky about getting that right. Like, we're really going to look at like that ordered pair 0, 1. So we'll circle back a little bit more to the logs later, but that is logs and more stuff on logs.